We are from N division group 7. In this video we are going to learn about Booth's multiplication algorithm. First of all, I am giving a brief introduction about Booth's multiplication algorithm. In this algorithm we have to multiply two signed binary numbers in 2's complement notation. This algorithm invented by Andrew Donald Booth in 1950 during his research on crystallography.
As we know that Booth's multiplication algorithm is used for signed and unsigned multiplication, let us now get to know the process for the same. We are going to understand it with the help of following flowchart. The first step here is initialization. We are going to initialize a with 0, q minus 1 with 0. Multiplicand here is stored in m, multiplier is stored in q. Count here is represented by m. The second step here is comparison between q0 and q minus 1. If q0 and q minus 1 is 1 and 0 respectively, then we replace a with a minus m. After that, we perform arithmetic right shift operation for a, q and q minus 1. After that, we replace count with count minus 1. Then we compare count with 0. If it is equal to 0, then we end the process. If it is not equal to 0, we again go to the second step, that is comparison between q0 and q minus 1. Now, if both of them are equal to 1 and 1 respectively, then instead of replacing a with something else, we directly perform arithmetic right shift operation for a, q and q minus 1. Then we replace count with count minus 1, and again we compare it with 0. If it is equal to 0, we end the process. If it is not equal to 0, we again go to step 2 of comparing q0 and q minus 1.
So now you know what exactly the Booth's algorithm is when it is 1 0 and 1 1. Here we go again. There's start. We see that accumulator A is 0. There's m, which is the multiplicand. There's q, which is the multiplier. There's count n. We go here, we check q0 and q minus 1 or 0 0 or 0 1. If it is 0 0, we simply go down, we perform the arithmetic shift right operation. That is, we shift it to the right by 1 bit. We decrement the count and store it in the count again, and we check if the count is 0 or not. If it is 0, we simply end it. If it is not, we go back to check what q0 and q1 is. Again, if q0 and q1 is 0 1, we come here, we add the accumulator with the multiplicand, and we store it in the accumulator again. We perform the arithmetic right shift operation, that is again shifting it to the right by 1 bit. We decrement the count and we see if it is 0 or not. If it is 0, we end it again. If it is not, we go again to where q0 and q minus 1 are.
See here, q0 and q minus 1 is 1 0. According to Boole's algorithm, if the value of q0 into q minus 1 is 1 0, we have to do a is equal to a minus m. Let us do a is equal to a minus m. For finding a is equal to a minus m, we have to take the second complement of m. M is the value is 7, so that we have to take the second complement of minus 7, which gives 1001. And after getting the binary of minus 7, we have to just add it in a, that is a is equal to a plus into bracket a minus m. So it gives the value of a is 1001. Q is as it is, and q minus 1 is as it is, and m is also as it is. After performing the a is equal to a minus m, we have to also do arithmetic shift right. We have to shift the value of a, q and q minus m, and count is equal to count minus m. We have to shift the value of a, 1 is here, and again 1 is here, 0 is here, 0 is here, this one is shifted here, and this 0 is shifted here, this 0 is shifted here, and this one is shifted here, and 1 is shifted here. Then our first operation or first cycle is completed. Then move on to the second cycle or second operation. See here, the value of q0 and q minus m is 1 1. So we, according to Booth's algorithm, we have to only perform arithmetic shift right on accumulator, that is A, Q and Q minus M. Let us do that one. Shift the value of accumulator. One is shifted here, and again one is shifted here, and this one is shifted here, and this 0 is shifted here, and this 0 is shifted here, and 1 is shifted here, this 0 is shifted here, this 0 is shifted here, and finally 1 is shifted here. In this way our second cycle is also completed.
So, so at the end of second cycle, we have 1110 in register A, 0100 in register Q, and 0111 in register N. Here the Q naught digit is 0 and Q minus 1 digit is 1. As per our flowchart given, uh, we should perform A equal A plus M operation. Uh, so we have to add 0111 in register A, which contains 1110, and store it in register A. 0 plus 1 is 1, 1 plus 1 is 1 carry 0, 1 plus 1 plus the previous carry 1 equals 1 and carry 1, and 1 previous carry 1 plus 1 equals 1 0. Here the fifth bit is discarded, so our register now A contains 0 1 0 1. Meanwhile, Q remains the same as 0 1 0 0. Q minus 1 remains also same as 1. Now arithmetic shift right is performed. Here all the digits are shift one place to the right. So this 0 is shifted here, 1 is shifted here, 0, this 0 is shifted here, 1 is shifted here, 0 here, 1 here, 0 here, 0 here. At the end of second cycle, the Q naught digit is 0 and Q minus 1 digit is also 0. So as per our flowchart, we should only perform the arithmetic shift right as in the fourth cycle. So this 0 goes here, this 0 goes here, this 1 goes here, 0 here, 1 here, 0 here, 1 here, 0 here. And this is the end of the fourth cycle. We have completed our multiplication. Here the answer is stored in register A and register Q. Final result is equal to data stored in register AQ, which equals 0001 0101. Here this equals 16 plus 4 plus 1, which equals 21, which is indeed 7 into 3. So we get our answer by using Booth's algorithm for 2's complement multiplication.
After learning about Booth's algorithm, here's an example to get you started. We have to do multiplication of 7 into 3. We know that the binary of 7 is 0, 1, 1, 1, and binary of 3 is 0, 0, 1, 1. In this example, 7 represents the multiplicand, which is denoted by M, and 3 represents the multiplier, which is denoted by Q. Let us try by Booth's algorithm method. The first column A represents the accumulator, which contains 4 bit. The 4 bit is always 0 in every example, and Q is our multiplier. The value of 3 in binary is written here, and Q minus 1 is the previous of Q naught, which is also 0 in a single bit, and M is a multiplicand, which is 7. The binary of 7 is written here. After denoting the initial value, let us perform the first operation.
So guys, this was all in our today's video. Hope you might have understood what is Booth's algorithm and how does it work. If you have any doubts regarding the Booth's algorithm, then please do comment below in the comment section. Before ending this video, we have some homework questions for you, and the answer to these questions will be provided below in the pinned comment. Hope you must have enjoyed the video, so please do like the video. If you are new to this channel, then do subscribe. Hope you might have also hidden the bell icon to receive notification about our upcoming videos. Also do comment about your doubts, and also comment which upcoming video do you need. So guys, this was all in our today's video. Till the next video, keep learning, keep exploring.